For your information, there's a lot more to ogres than people think.
Example?
Example? Okay, ogres are like onions.
They stink?
Yes. No.
Oh, they make you cry?
No.
Oh, you leave them out in the sun, they get all brown, start sprouting little white hairs.
No. Layers. Onions have layers. Ogres have layers. Onions have layers. You get it. We both have layers.
Okay, let's be clear that this is extremely fast electron configuration because we're trying to just get right down to nuts and bolts. So let's start. Please notice that we have a Bohr diagram here, which I'm going to use to visualize where the electrons are located at the same time that we watch the periodic table. I'm going to number 1, 2, 3, 4, 5 rows down the periodic table. And so let's start with the very first element, hydrogen, with its 1 electron and 1 proton. We put 1 there, and the first electron would be in the very first energy level. I don't know why it doesn't say first here, and so we would write 1s1, meaning energy level, orbital type, and this, of course, would describe the actual electron. If we carry on to helium, which of course you'll notice is way over here in the periodic table, but notice that I've outlined this area. Helium, in fact, should be here. Let's talk that this area of the periodic table is the S block. This area we're a ways from getting there, but is the D block. And over this area to the right, we would have the P type of orbitals. And so even though helium is over here, we have to remember that helium is, its electron is in an s orbital. So we would simply change the electron configuration to 1s2 to represent the 2 protons and the 2 electrons in helium. Let's progress very quickly to lithium, which we would change then to 3 electrons, 3 protons. And so the 2 electrons would go in the first energy level and 1 more electron. There's no room in the first energy level. It's too small to contain any more than 2 electrons. So we'd have to write 2s1 to once again represent the 3 total electrons. Beryllium, not much different. And we would continue on and say, okay, beryllium with its 4 electrons, we would change this the number of electrons in the, let's fix that again, number of electrons in the, to be a total of 4, so we'd have to change to S2, and so we'd have 2 electrons, a total of 4 protons, and that would represent beryllium. Notice, of course, as we progress across the periodic table, there's nothing in the D area at this point, so we, of course, as we move to boron, we notice that we are now in the P block, and so we would have to write a P orbital. We're still in the second energy level, and we would have 1 electron. If we continue to carbon, and so we'd put that 1 electron, 2 electron, let me change to red, 2 electrons would be in the S orbital, 1 in the P, for a total of 3 electrons in the second energy level. If we carry on to carbon, nitrogen, oxygen, let's go all the way across to oxygen. That would be counting if you had 1, 2, 3, 4 across. That would mean, of course, that we would have 4 electrons in the P, 4 total electrons, and so we would have to change the number of electrons in the second energy level to a total of 6. Where am I getting 6? 2 in the S orbital, 4 in the P, 6 valence electrons. There they are, 6 valence electrons. This is just the breakdown over here, but ultimately 6. And let's do magnesium with its 12 electrons and 12 protons. Of course, we would start with, let's write a condensed. And when we write a condensed electron configuration, we go up 1 level and go across to the last noble gas. So that would make us want to write neon. Square brackets, of course, means all the electrons of neon. And then we would write 3s2. Then we need to immediately proceed and move across the periodic table. Let's pick out sulfur, for instance. And so sulfur, with its 16 valence electrons, we've got 10 electrons accounted for here. So let's erase and put a 16 in here. So we've got 16 protons. We have 2 electrons in the first energy level, 8 in the second, and we already see an S2. And so the rest of the electrons for sulfur, of course, will end up in the 3p, and it is 4 columns across in the p block. And so we'll notice that we'll write 3p4. So we'll write a 4 here for a total of 6 valence electrons. Now, that would continue on if we were to finish up with argon. I'll do it in blue. If we were to finish up with argon, we would, of course, write P6. 3p6, number of electrons would change to 8. And, of course, we'd have 6 electrons in that P. And so then it's time to move down to potassium and calcium. And so we would continue, and we could use, this time, of course, we can erase, and we could, if we were writing a condensed electron configuration, condensed, if AP asks you to write an electron configuration, you can write either the whole thing or condensed, but we'll continue with condensed. And so that means if we're trying to write a configuration for potassium, we should move up one row and pick the last noble gas, which of course is argon. And so we would write argon in square brackets to represent all of its electrons, and 4s1, which would mean one more electron out here in the 4th energy level. If we wanted to change that calcium, we would write 4s2, s2, and we would change this to s2. That would be calcium. Now, this is where we really need to be careful, because here, the division between the S and the D block, we have to notice that there is a D set of orbitals in the 3rd energy level, which we didn't use yet. And so what's going on with that? It so happens, if we now are referring to scandium with its 21 protons, it so happens that 21 protons is enough attractive force to pull the 21st electron back into a d orbital that is in the 3rd energy level. So the electron that we might have thought we should put out here in the p is actually pulled back and replaced and put into the d orbital. So for scandium, we would write 3d1. If we were to continue all the way across to nickel, which of course is d8, we'd still stay 3rd energy level, d8, and that of course would bring us up to a total of, here I'm going to erase, that would give us a d8 here, which would mean a total of 16 electrons in the 3rd energy level. Some of those are not showing, of course, because they're part of argon, but then the 8 d electrons for nickel. If we continue on, and we maybe move across to, say, arsenic, we would be back in the P block, and of course we're in the 4th energy level. So, well, I should say first we'd have to finish with D10 would bring us to zinc, and then we would need to continue in the 4th energy level with 4p. If we were wanting to finish with arsenic, we would say 4p3. We could carry on quite similarly with krypton, which would end us with, if you allow me to erase, would end us with 4p6 with a total of 18 electrons we would have by now, and we would now be back to 6 valence electrons in the fourth energy. Sorry, that's not true. Let's change that to 8 valence electrons, 6 in the s, 6 in the p, 2 in the s, for a total of 8 valence electrons. Okay, here we go. Let's wrap up our treatment of electron configuration, say with tellurium, element number 52. And let's write a condensed electron configuration. It's certainly much too big to be bothered writing the complete electron configuration. Of course, to write a condensed, we back up to one row above. We would proceed and write down that noble gas, which of course is krypton, put it in square brackets, and then we would carry on in the fifth row of the periodic table. We need to first account for the 5s2 electrons. They would be out here, s2. Probably should have just written that. And then we would notice that now we were in the D area of the periodic table, and to get all the way over to tellurium, we would need to put 10 electrons in the d orbital. Let's not forget that there was something very special about the intersection between the s and the p, and of course these electrons now are put down into the 4d 10, and then to finish, to get to tellurium, we need to go back out to the 5p and place 4 electrons. There'd be 10, of course, down here in the d. These, of course, would all be filled with appropriate number of electrons, represented, of course, by krypton. So 5p4. Now's a good time to talk about something known as orbital notation. Orbital notation means write a circle or a line to represent each orbital in the subgroup. So these 5 circles or 5 lines are representing my d electrons. This is representing my s electron, and then I'm a little bit beyond, but I'm going to finish with 3 more circles in 3 lines, or 3 lines. You could do either or. And to represent the p orbitals. It's not very interesting except when we get to the p. The s, I would draw one line to represent 1 electron, a second line to represent a second electron. Generally, they're represented with up and down arrows. Electrons have a property known as spin, which AP is not likely to ask about. And so the D's are also very boring. I'm going to fill up the D's, and while it doesn't really matter how I fill them now, it is true that each D orbital would get 1 electron, 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10. Because it gets really interesting when we move out to this P and we only have 4 P electrons. It's really important to notice that the P electrons will spread out as much as they can within the P subgroup. And so in that way, and it doesn't matter where you pair up the fourth one, that will be important later that we understand that orbitals, sorry, I didn't mean to say orbitals, electrons will spread out within a subgroup. That's it for now. Practice up.